Hey guys, welcome to the last module of this learner space course on device physics. Today I'm going to talk about MOS devices, and like as promised in the beginning of the course, we are going to finally understand how a MOSFET works. So hope you guys are looking forward to it. Today, the stuff that I've covered, many of the slides are borrowed from Professor Swarup Ganguly when he taught the device physics course in spring 2025 semester. Okay, so the first thing I want to do before we get into the MOS devices, I want to cover two more like two more things we use when we draw band diagrams. You can call them what you want. You can call them terms we use or definitions we have. So it's the work function and the electron affinity. So the essentially whenever we are talking about any energy band diagram, we're always talking about the energy with respect to some reference level, and that reference level is called the vacuum level. And generally we assume that electrons are completely free in that reference level and they're not bounded by any atom, right? So the work function is basically just the energy difference between the vacuum level and the Fermi level. So it's just a definition. There's no need to like go into any intuition for it. And similarly, the electron affinity is the energy difference between the vacuum level and the conduction band energy level. So yeah, it's just two definitions. One, work function, difference between vacuum level and Fermi level. Second is electron affinity, difference between vacuum level and conduction band energy. Now for metals, the Fermi level and the conduction band are drawn in the band diagram at the same place. The reason for this is because, as we discussed in one of the very earlier lectures, which was that metals have these semi-filled conduction bands, so that makes them very good conductors because they have a lot of these empty states in their conduction bands that the electrons can go into. So since they have partially filled conduction bands, and we're talking about 0 Kelvin, so at 0 Kelvin the highest filled state is where our Fermi level will be. We know this from the definition of Fermi level. So if the Fermi level is at the highest filled state and the highest filled state is in somewhere in the middle of the conduction band, and when we are drawing band diagram, we generally ignore the thickness of the band itself. We assume that the band is of like the thickness of the order zero point 0.1 eV or something like that, zero point 0.1 electron volt. A small amount which we ignore, and the Fermi level is inside that band. So when we are drawing this band diagram or for metals, remember because metals have these semi-filled conduction bands, the Fermi level and conduction band are shown as same and are considered to be equal. So as a consequence of this, the work function and electron affinity are also the same for metals. Yeah, so this is just some stuff I wanted to cover regarding these two terms. I just want to avoid confusion. So the thing is that conventionally different sources have treated work functions and electron affinities interchangeably, as sometimes treated them as voltages and sometimes treated them as energy. So you might have the work function of a metal represented to you as 3.5 volts, or you even might have it represented as 3.5 electron volts. So depending on that, in some sources, either they might directly be using it as the energy, or they might be multiplying by the electronic charge and using it as the energy. My point to say this is just that if you see different stuff at different places, don't get confused. I might even use them interchangeably in the slides depending on what source I am picking up what figure from, for example. So based on the context of the situation, whatever is making sense, just feel free to assume that. So before getting into the band diagrams and the analysis of the MOS, first I want to talk about what a MOS is and why we care so much about it. That in the whole course was also building up to a MOSFET. So MOS basically stands for something really simple, metal oxide semiconductor. So it's literally like a layer, three layers of materials, one metal, one oxide, and one semiconductor. So metal behaves like a conductor, oxide behaves like an insulator, and then you have a semiconductor. That is all there is to a MOSFET. Cool. Now, why do we care about the MOSFET? Is because the configuration of the MOS can, according to the voltage applied to the metal, with respect to the rest of the device, this configuration can control the formation of a conducting layer across the device called an inversion layer in the semiconductor, which is capable of conducting current. So basically, uh, there is a layer in the device which is capable of conducting current, which can be created or destroyed based on the voltage you apply to the metal. And this is why it's of prime interest to us, because we can use the voltage applied to the metal to turn this device on or off. Because if there is a conducting layer and we apply a voltage across the device, it's on. If there is not a conducting layer and we apply a voltage across it, it's off. So since we can control the formation of this conducting layer across the semiconductor, we essentially can control the on or off state of this MOS device using the voltage at the metal or the gate. And this is why we care about the MOSFET, because essentially we want to make a switch, remember? Yeah. So that's why we care. Cool. So now I want to talk about an ideal MOS structure with flat bands. So first, I just want to get into the definition of ideal MOS, an ideal MOS, and don't get intimidated by this diagram. We'll then get into this diagram slowly. Cool. So the definition of ideal MOS is pretty simple. It's just that the work function of the metal and the semiconductor are equal. So for the metal, this is the Fermi level as well as the conduction band edge. We discuss why they're equal. For the semiconductor, this is the Fermi level. And since the distance from the vacuum for both the metal as well as the semiconductor are same, this being the vacuum level, this MOS is called an ideal MOS. Now, as you can very clearly see, we have like these different quantities over here. You have this work function, can have electron affinity for the semiconductor, for the insulator as well as for the metal. Now, as you can clearly see in this diagram, since phi m and phi s are equal to each other, which means the work functions are equal, which means that the vacuum level is at equal distance from the Fermi level, both for the metal as well as for the semiconductor. Uh, that means that our Fermi level throughout the device is flat, which means it's same at the metal as it is at the semiconductor. So, uh, given that the Fermi level is flat, this entire situation is in equilibrium, and we have no issue with it, right? Because we know that at equilibrium our bands are flat, Fermi level is same on throughout the device, and we don't have any applied voltage. So this particular type of MOS device is called an ideal MOS, because both the work functions are equal, and that means that without doing anything externally, you will have this type of band diagram where all your bands are flat. Cool. So, yeah, that's the base. This is essentially just the band diagram of this MOSFET. And remember, the oxide is the insulator. So, this is the electron affinity of the oxide. This is the electron affinity of the semiconductor. This is the work function of the metal. This is the work function of the semiconductor, etc. So you can see that. You can also see that the Fermi level is closer to the valence band, which makes sense because it's a p-type semiconductor. And this lighter line in the middle is meant to indicate the intrinsic Fermi level, which is roughly in the middle of the conduction band and the valence band edge. Cool. So I hope this structure is clear and the definition of an ideal MOS is clear. Uh, Assuming it is, I'll move on now. Cool. So now that we've spoken about an ideal MOS, I want to spend some time on talking about non-ideal MOS devices. Now, the thing with non-ideal MOS devices is that your work function on both sides of the like the metal and the semiconductor are different. What that essentially means is that the distance from your vacuum level for the Fermi level, the distance of your vacuum level from the Fermi level on the metal side and on the semiconductor side is different. Now, given that it is different, you have two options. Either you can have the Fermi level equal in the metal as well as in the semiconductor, and to accommodate for the fact that the work function is different, you your vacuum level needs to bend across the device, which I will come to in how that bending actually looks. That's one way that this can be reconciled. The other way, the fact that you have a different Fermi, like you have different work functions on both sides, meaning different differences between vacuum level and Fermi level on both sides, the metal and the semiconductor. The other way you can resolve this is by saying that, okay, uh, the work functions are different, so we'll just have different Fermi levels for the metal and the semiconductor. Now, the first approach where we say that okay, we have equilibrium, so and we are not applying any external bias, so we have equilibrium and we have a flat Fermi level throughout the device, which is the same at the metal as well as the semiconductor. We need to allow for the vacuum level to bend so that supposing the work function of the metal is more, then the vacuum level bends down as it reaches the semiconductor. Also, one important thing to note is that the work function is defined for an isolated material. So when you have these materials interacting with each other, the definition is likely to be valid far away from the junctions. So in the semiconductor, when you're talking about the work function, you're going to calculate it far away from the oxide that it behaves like a pure semiconductor. Yeah, so that's why that's something I wanted to get out of the way as well, because that's why your band bends and eventually reaches a level where the difference with the common Fermi level is the same, is the work function of the semiconductor and less than the distance of the vacuum level from the Fermi level in the metal side. So that's one way you can do it, where you allow the vacuum level to bend. The the consequence of that is that when your vacuum level bends, since your conduction band is always defined in reference to your vacuum level, and your valence band is also always defined in reference to your vacuum level, those bands as well in the semiconductor start bending. Now, essentially, the first condition that we want to solve for is the flat band condition, where all our bands, be it the conduction band, valence band, they are all flat. So clearly, this solution of having this constant Fermi level throughout the device and letting the vacuum level bend is not making sense here, because we want to first solve for the case where we have flat bands. The reason we are so interested in flat bands is because flat bands kinda represent like flat bands basically means that the energy is constant, which means that there is no there is no tendency for electrons to move from some high energy region to low energy region or vice versa. So because of the stability of the flat band situation, we or equilibrium of the flat band situation, we try to create this flat band. So now we are only left with the second alternative uh, to reconcile this difference between the work function of the metal and the semiconductor. And that second option is essentially you let the Fermi levels be different. Now, what happens when the Fermi levels are different? Supposing the Fermi level of the metal is lower than the lower in energy than the Fermi level of the semiconductor. Now, to maintain this different Fermi levels at different parts of the devices, we must apply a voltage. Why is this the case? This is the case because if you have low Fermi level at the metal and high Fermi level at the semiconductor, for example, keeping a fixed vacuum level so that your phi m and phi s expressions are able to match, what that essentially indicates is that electrons are more comfortable being pulled towards the metal from the semiconductor. So essentially, there is a tendency for electrons to move from the semiconductor towards the metal. And the only way that we can physically ensure that is that we apply an electric field across the device. So what I'm trying to say is that uh, the Fermi levels being different, a lower energy Fermi level at the metal, a higher energy Fermi level at the semiconductor, means that electrons from the semiconductor are pulled towards the metal. And the only case in which that can happen is when you have a electric field, and the electric field is born from a voltage. So the only way in which a flat band is possible is if you externally apply a voltage to create that flat band situation of the electric field that is able to pull the electrons from the semiconductor to the metal. So this is why for having flat bands, it is absolutely essential for this voltage, external voltage to be applied. And the voltage that we apply to get these flat bands is called the flat band voltage. Uh, the exact value of this voltage is something I'll get into in a bit. I'll just move on to the next slide. This is what I was talking about earlier, which is that this conduction band and valence band follow the vacuum level and also would bend in response if the vacuum level were to bend. So if we want flat bands, the Fermi levels will have to be different in the metal and the semiconductor, and we need some physical effect that justifies this difference. So the physical effect that can justify the difference in Fermi levels is only an external voltage source. So we get this physical effect by applying a voltage at the metal that can justify this difference phi m minus phi s, which we call phi ms. So to justify this difference of Fermi levels, we apply this voltage phi ms on the metal side. What that essentially does is that you're basically say your metal is having a work function of 5 electron volt and your semiconductor is having a work function of 3 electron volt. Now you need some electric field that is justifying this 2 electron volt difference. And that electric field which you the voltage that you need to apply to generate this electric field will be 2 volts on the metal side to actually show that the electrons are being pulled towards the metal. So again, it's phi, this is the voltage, phi m minus phi s that you need to apply. Now, of course, the units is something you have to be careful of. If it's electron volts, then you have to divide by the charge of the electron to get the voltage. If it's just volts, then this gives you the flat band voltage that you need to apply to in order to get flat bands. So yeah, this is the flat band that you actually get. As you can see, phi m is the difference between this Fermi level and the vacuum. Phi s is the difference between this Fermi level and vacuum. You have a difference in Fermi levels, the magnitude of which is phi ms, and this difference in Fermi levels can only be explained given that electrons are going to want to move from here to here. If you have an electric field from the left to the right, and that can only be created if you apply this voltage of phi ms from the left to the right. That is the explanation that we've given so far. And because your vacuum level is flat, your conduction band is with respect to the vacuum level, that is also flat. Your valence band is with respect to the vacuum level, that is also flat. Now, these are just some calculations that they did based on these differences. It's not important. It's just adding up these energy levels and equating them. So yeah, I'm not gonna get into these calculations. Cool. So we've spoken about the fact that you need to apply this voltage in order to keep the bands flat so that you can accommodate this difference of Fermi level. Now we're going to talk about what happens if we don't apply this required voltage to keep the bands flat. And this is what we call band bending. Again, don't let yourself get intimidated by the diagram. I'll go by it step by step. Cool. Uh, Now, uh, I want to start explaining this band diagram. But the first thing I want you to notice is that now that we are not applying any external voltage, means there is not gonna be any external electric field. If there is not gonna be any external electric field, that means that there is no physical cause that can justify a tendency for electrons to want to move from one part of the device to another. And if there is no cause, then that phenomena will not happen. So electrons are not going to prefer any part of the device now that you don't have any external electric field pushing it to do that. The thing that comes up due to this is basically that you're going to have flat Fermi level throughout the device. Because if your Fermi level at any part of the device is higher than some other part of the device, then your electron is just gonna want to flow from the high energy state to the lower energy state. So because we don't have any external voltages or electric fields, the electrons must, the Fermi level must be flat and constant throughout the device. So that's the first thing I wanted you to notice. Second thing, always in the band diagrams, whenever you're drawing band diagrams or analyzing band diagrams, the best intuition is to the best intuition to get is from the extremes. So you can see that at the extreme left, you have a pure metal. So this band diagram is going to look just like a metallic band diagram where this is the Fermi level, this is the vacuum level. At the rightmost extreme is going to look purely like a semiconductor. So this is the precise band diagram of a p-type semiconductor. Now, what I want you to notice here is that we are talking about a non-ideal MOS device, which means that phi m and phi s are unequal. So now at this point where you're very far away, you're behaving like a pure semiconductor. So your difference with the vacuum level is going to be precisely the work function. So this difference between EF and the vacuum is going to be the work function. And over here, the difference between EF and the vacuum is going to be again the work function of the metal. Now you can clearly see that if the work function of the metal is more than that of the semiconductor, then somewhere in the middle, this vacuum level needs to bend downwards to bridge that gap, right? And that bridging that it needs to do is what we call band bending. Now this bridging is essentially done in mainly two two regions. Part of it is done in the oxide, and part of this bridging or band bending happens in the semiconductor. And when you get far enough away from the edge, this band becomes flat. And obviously, this conduction band and valence band follows the vacuum level because it's defined with that as the reference. Cool. So to keep a flat Fermi level, you needed to have a vacuum level that bent, and that caused these bands also to bend. Uh, cool. So what then we want to answer is that why is this band bending linear in the oxide? And to answer this question, I want to note to you that this band bending is kind of how the energy is moving, and we know that energy and voltage are proportional to each other, so this is kind of how the voltage is moving. We know that the electric field is the derivative of voltage. So linear band bending basically just means a constant electric field. Now this oxide or insulator is of such a type that you essentially have you can have charge on its left, you can have charge on its right, but you can't have charge inside it. Which means that the electric field, according to Gauss's law, if you take any surface inside it, the electric field going in has to be equal to the electric field coming out, because you won't have any accumulation of charges inside the oxide. Which means you're going to have a constant electric field inside this oxide, which means that your band bending has to be linear. So this region sees linear band bending, and the semiconductor can see non-linear band bending as well, which is why we've depicted it this way. And yeah, so that's essentially uh, the how the bands bend in order to keep the Fermi level flat, while also have reconciling this difference of work functions, where this work function is smaller than this work function. And essentially that's what they're saying, that the difference in the individual Fermi levels when you had kept them apart from each other and the vacuum were at the same level is equal to the difference in the work functions of the two metals. Cool. And this is also the voltage that you would need to apply on the left side to get flat bands. So that's also what we call the flat band voltage. So this is what happens when you don't apply any voltage or sufficient voltage to the MOS device. Right, cool. Uh, Now I just want to talk about some cases of band bending. Uh, Either you can perfectly account for it, like we did in the case of flat band, which we've already seen. Uh, Secondly, you can reinforce the band bending by the voltage you apply. Like if you apply a negative voltage, the bands are going to have to bend even more because the Fermi levels are going to go like this. So you will need to have even more band bending to account for it. Or if you try to account for it, but you're under accounting. So if you try to apply some voltage, but that voltage is not enough for the bands to actually uh, become flat. So this case is called accumulation. And the third case is that you over account for band bending, which means you apply even more voltage than the flat band voltage. And what that does is that it causes the bands to essentially bend in the opposite direction. And this over accounting has two sub cases, which I would like to talk to when I get to, because I don't want to uh, give too much information and confuse you now. So I'll talk to you about those two cases when I get to it. But essentially, you're just applying so much voltage that it's causing the bands to actually bend in the opposite direction. Cool. So we'll get into these cases one by one now. Before we get into these cases, I just want to mention something that you don't get confused when you're viewing the slides. In some of the diagrams, they've shown a direction of the gate voltage as being pointing in some direction, which you might interpret as, say, positive or negative or whatever. I would either tell you to mentally invert the arrows or just like not view those arrows. I think it was a mistake, or maybe I don't have the context in which that was given, but it might be a bit confusing, so I'm just apologizing in advance, and I'll tell you about it when those diagrams come up. I just like the diagrams, so I picked them up from there. Cool. Cool. So before we get into accumulation, in these type of diagrams, I just want you to avoid the trying to read what these arrows mean. It can just get a bit confusing, and it's not important for the discussion we're trying to have. What I'm essentially just trying to show you is the shape in which the bands bend. That's literally all I care about, right? Cool. So, uh, the accumulation case which I spoke about, which is that we don't have enough positive voltage. We know that we need the 5 ms amount of voltage to make the bands flat. So we don't have that, which means the bands are still bent. Now this can mean that you apply a very small positive voltage, you apply no voltage, or you apply a negative voltage in which the bands will be bent even more. But all these cases amount to accumulation. Now, given that we know that these bands are bending in this way, right? This is the vacuum level, for example, it's bending downwards. We know that this band bending essentially implies an electric field. So, if electron energy is reducing from left to right, let's talk about the oxide specifically. If electron energy is reducing, then uh, for like positive charge energy or voltage, which is conventionally defined with respect to positive charge, is essentially increasing like this. And we know that to create an electric field, to create a voltage difference, you need an electric field that pushes from high voltage to low voltage. So we know that this point, since it has high electron energy, it's going to have low voltage, and since this has low electron energy, it's going to have high voltage. So we are going to have an electric field that's pushing from high voltage to low voltage, and the so we need some way to create this electric field, right? We can't just say that, oh, the bands are bent and call it a day. We need to figure out what the source of the field is, and since we are not applying anything externally, the only way this field can be created is internally, and that is what we are trying to figure out, how this charge is going to be redistributed internally for that to happen. Now, in terms of what the metal can do, the metal can do something really simple. The metal knows that it needs electric field from right to left. So to justify the way the band needs to bend, the metal needs to redistribute its charge such that electrons come near the edge. So metal has a lot of free electrons. It knows that electric field is needed from right to left to, what do you say, uh, have the bands bend this way. And if you want to ask, by the way, that why is this tendency there for the bands to bend this way? The answer to that is that this is the only way the Fermi levels equalize. So that is why the rearrangement is going to happen in a way so that this band bending becomes physically possible. Now that becomes physically possible only if you have electric field from right to left. And the only way that field gets created is if metals push the electrons like this. Now these electrons are obviously going to now go ahead and attract holes from this p-type semiconductor, and these holes are going to accumulate like this. So this oxide layer is essentially like a capacitor, and you have some charge accumulated here and charge accumulated here. So this is the way we get this charge distribution and accumulation. And because you have accumulation of charges at the surface, that is why it's called accumulation. Yeah. So I hope accumulation is clear. I want to move on to the next part. Cool. The next thing so I want to talk about is depletion, which is the opposite of accumulation in the sense that this time you're over accounting for band bending. You have given a positive gate voltage that is even more positive than the flat band voltage 5 ms, which means that now you are essentially bending the bands in the opposite direction. So we have more positive voltage than we need for the bands to become flat. This excess positive voltage is going to draw electrons away from the metal and leave this rightmost end of the metal positively charged. This is also the only thing that the metal can do to explain this type of band bending. Similar explanation as to what we had on the last slide. So you're going to get a positive charge here. This positive charge is essentially going to repel holes away from this P-type semiconductor. So when it repels holes away, it's not able to create a concentrated surface charge and balance this positive charge this way. It repels holes away, and as you know, the P-type semiconductor is going to have these ions, negatively charged ions. So when the holes get repelled, those ions get exposed, and this entire a region gets depleted of positive charge, and you have these negative charge ions remaining. The depletion region will last for as long as this negative charge perfectly balances out this positive charge. So essentially this time you don't have accumulation of surface charge because you don't have negative ions to essentially go by, but you have this depletion which balances out this surface charge. Yeah, so this is how we explain this depletion in terms of this charge separation thing. So obviously anything that happens in the bands has to have a physical effect. You Bands don't exist in real life. Bands exist in our model of the situation. But things like electrons, things like these holes and all that exist in real life. So we have to we have to find the things that exist in real life that cause the things to happen in our model. Yeah, so this is depletion. I want to move on to the next part. If you remember, I told you that in terms of over accounting, there are two cases. So, first of those cases was depletion. Now, I want to move on to the next case, which is inversion. Sorry, before I move on to inversion, sorry about that confusion. I'm going to just do some calculations related to depletion. Now, obviously, you know that the gate voltage is more than the flat band voltage. The flat band voltage itself is equal to 5 ms. They've spoken about there being some extra terms here, but that is beyond the scope of our discussion right now. So we are just going to stick with the flat band voltage being equal to 5 ms. Now, we know that in this gate voltage being more than the flat band voltage, the rest of the voltage has to be deposited somewhere. So some of that excess voltage is deposited across the oxide in this Vox, and some of this excess voltage is deposited across the semiconductor in psi s. So essentially this delta and this delta is the overhead of the gate voltage above the flat band voltage. So that is what this equation is essentially telling you. Now, another thing to notice is that when you see this depletion, it should remind you of something that you have seen before in the last lecture. And the thing that it should remind you of is a PN junction. So even in PN junction, you have the middle of the junction getting replaced. So you have a P, you have an N. Part of the P gets depleted, part of the N gets depleted. Now imagine, say you have a N and a P. and part of the N gets depleted, part of the P gets depleted. Now imagine your N is extremely highly doped. What that's going to mean is that you need very less depletion of the N region to deplete a lot of the P region and still maintain charge neutrality. So what that means is that when you have a very highly doped NP junction, most of the depletion is going to happen across the P junction. And I want you to bring your attention now to our situation that we have here, where we have all the depletion across the P region. So does it not make sense to you that we can model this P region as being part of a one-sided PN junction where the N was extremely highly doped such that all the depletion happened across the P. So all I'm trying to tell you is that it's mathematically equivalent to having a one-sided PN junction, because if you had a N over here that was extremely highly doped, it would not change anything over here. It would create exactly this type of situation. And because it's mathematically equivalent, we can use the width and surface, essentially the relationship between width and voltage to actually relate psi s to the width. And we use the diode formula that we derived in the last class for this, because we essentially approximate this P as being part of a one-sided PN junction where the other end is so extremely doped it's as if it didn't exist. I'm sorry if that confuses you a bit, but we just want to invoke the formula that we derived over there. So if you're a bit confused, maybe you can listen to the explanation again or reach out to me. Cool. So this is the formula that we had in the diode, which is that the voltage is related to the width this way. So now we have this relationship between the voltage and the width. Remember, this is the voltage across the depletion region. We again assume that all the action happens across the depletion region and not much of the band bending happens beyond that. Cool. Now we also know one thing, which is that Q across the semiconductor is the charge across the semiconductor is essentially equal to the depleted charge, because that's where the charge comes from. And one thing I want to note here is that the Q that we are using here is actually charge per unit area. So even though the symbol uses Q, we are talking about per unit area. So if you want charge per unit area in depletion, you know that in depletion, the charge per unit volume is left by just these ions. Na is the concentration of ions. All the holes have been depleted away. So those don't contribute any charge. It's just that these ions that contribute charge. Each individual ion per unit volume contributes, these are the number of ions per unit volume. This is how much charge each individual ion contributes, and this is the length. So the product of the three cumulatively is going to give you the total charge per unit area, which is what we want, which is the calculation we wanted to do for this depletion region. And using this formula, we can essentially substitute the width in terms of this voltage across the semiconductor, and we get this expression that relates this charge charge to this voltage across the semiconductor. So yeah, that's some calculation which becomes useful to us in the future. So we are doing it now, which is basically just the charge per unit area in the depletion case. Cool. Moving on. The next thing that essentially I want to bring to your attention is that this oxide, behaves essentially no different than a capacitor. So you can think of this exactly like a capacitor. Uh, and a fair warning again, the symbol here we use, that which is C ox or capacitance of the oxide, is again per unit area. But then when we do charge per unit area divided by capacitance per unit area, the per unit area gets cancelled out. So anyway, the capacitance of this oxide per unit area can just be represented by the standard parallel plate formula for capacitance, which is epsilon by thickness, right? So that's the capacitance and the voltage across this oxide layer. So we spoke a little about the voltage across the SiS, the semiconductor. Now we can write the voltage across the oxide layer also purely in terms of the charge, because if this is the charge in the depletion region, it's also the charge on this surface divided by the capacitance, and based on that we get this formula for the voltage across the oxide layer. So we are able to essentially write about the voltage across the oxide layer as well as SiS as well as the flat band voltage and equate all of that to the gate voltage. Cool. We can clearly see that the oxide voltage has a root of voltage across the semiconductor dependence, so we kind of get this type of dependence. The rest of the formulas on this page are not that important. So just we are doing some quantitative analysis with respect to depletion before moving on to inversion. So the next thing that I want to talk about is, as I said before, the second type of phenomena that happens when you overcorrect, which is inversion. So we spoke about how when you apply voltage more than 5 ms, you start having this band bending of the opposite kind. Now when you keep doing that, look what's happened in this case, right? Focus on the extreme left where my pointer is pointing right now. If you see, the Fermi level is now closer to the conduction band than the valence band. And this is essentially at the extreme left behaving more like an N type than a P type. So essentially, the more and more band bending you have, the stronger the voltage you apply, the more and more band bending you have. The surface of the semiconductor starts to become more N type when you view it relative to the Fermi level. So we know that when Fermi level is close to conduction band, that is more N type, and when it's close to valence band, it's more P type. Now we somewhat arbitrarily define a threshold voltage, which we call the voltage beyond which the surface becomes more N type than the bulk is P type. And we then say that beyond this threshold, inversion has occurred. So let me just explain you what exactly I mean by this. So if you look at this difference between, say, the intrinsic Fermi level and the Fermi level, that kind of gives you a clue as to how p-type this material is, right? The further away EF is from EI, the more p-type the material is, because the closer EF is to EV, right? So when your intrinsic Fermi level, which by the way bends the same way as your conduction and valence band, when that intrinsic Fermi level bends in enough so that this difference becomes equal to this difference, or like supersedes this difference, that essentially means that here how N type you are is more than here how P type you are. And we essentially say that the semiconductor near the surface has become inverted and is behaving like a N type. And we call this phenomena inversion. So let's talk now about the consequences of this phenomenon. So when you have this inversion, you can continue increasing the gate voltage, which essentially is going to make the band bending even more, which is going to take your Fermi level closer to your conduction band closer to your Fermi level, which means that it's going to become even more strongly N type, which means that at some point it's going to become very highly conducting. And so more and more you apply the gate voltage, more and more can this layer uh, near the oxide conduct. And this layer is what we call the inversion layer. And it is the creation of this conducting layer that can turn a MOS device on or off. What do I mean by this situation? What I mean is that when I increase this gate voltage a lot, it creates a N-type material over here, right? That N-type material, uh, what do you say? That N-type material becomes more and more conducting the higher this gate voltage is, because it becomes more and more strongly doped. It behaves more and more like strongly doped N-type material based on its bands. So the more conducting it becomes, if I connect now two terminals, a drain and a source, and I apply a voltage across it, now this channel that has formed near the surface due to the phenomena of inversion that we just discussed can conduct voltage across the drain and the source. So the creation of this conducting layer is controlled by the gate, and the conducting layer itself can conduct current. So based on whether the gate voltage is above the threshold for inversion by some significant amount, this conduction can happen freely. So that is why we have this thing called inversion layer. And this is essentially how a MOS device works, which is basically that when your gate voltage is more than the threshold, this inversion layer gets created, which can conduct when you apply a voltage across the drain, this being the drain, this being the source. If you apply a voltage across it, this layer can conduct because it's become extremely N-type because of the band bending. So I hope it was clear. I think if I'll continue repeating it, I'll be going in circles. So if I was unclear, just go back and rewatch it. This is kind of the crux of the matter we are trying to discuss. So if it didn't make sense, I would highly recommend you to rewatch the last couple of minutes. Cool. That being said, let's move on to the next slide. So yeah, this is the basic principle of operation of the MOS device. So just understand it well. Cool. So now we want to evaluate this a bit more quantitatively. Cool. So sorry, we spoke about the threshold voltage or this inversion occurring being at the point where this part becomes more N-type than this becomes P-type. And the way to quantify that is essentially that this difference that you have between this intrinsic level and the Fermi level, intrinsic Fermi level and the Fermi level, if that gets equalized here, if the bands bend so much that it gets equalized here, then this is as N-type here as it is P-type here. So beyond this point, that gets essentially inversion, quote unquote, inversion occurs. So we know that psi s is this net band bending. Just please note very carefully here that psi s is not the distance between the intrinsic Fermi level and the conduction band as it might appear. If you can even go back through the previous slides where psi s was defined, it is the net voltage that comes across the semiconductor. So it's this maximum minus this minimum is what psi s is. And we know that this part is phi f. I'm gonna call this symbol phi because I don't know what it's actually called. So this symbol is phi f. This symbol is also phi f. So this inversion occurs when psi s is equal to 2 times phi f. This phi f is just the difference like very far away between the intrinsic Fermi level and the Fermi level in the p-type. So it's a property of the material itself because far away this band bending and all doesn't matter. So at threshold you have psi s equal to 2 phi f. Now we essentially want to calculate this threshold voltage, that what is the voltage I need to apply at the gate in order to create this inversion layer or have this phenomena of inversion. So for that, first let's discuss this charge distribution and inversion. One is the charge that you had due to depletion, which was anyways there. And the second thing you get is that because of these N-type material, you get an accumulation of electrons over here. So it's essentially this both coming together that form your charge. Now, these both come together and act across this capacitance basically, which essentially gives us this formula, which is that the we know that Vg is the flat band voltage plus what went across the oxide plus what went across the semiconductor. Now what went across the oxide can be written as the charge due to depletion plus the charge due to inversion upon the oxide capacitance. Now uh, this this is the this is true for all cases of inversion, but for the threshold, which is the first voltage at which inversion starts, we are essentially talking about the case where psi s is equal to twice phi f, because this becomes then as n-type as this is p-type. Cool. So, of course, we've seen the formula for depletion before. We know that it's a function of psi s. So, that is totally cool. Uh, we don't know how to write this inversion charge, but that is also a function of psi s. But now for the threshold voltage, we know that psi s is twice phi f. So, we can just substitute that in, right? And it so turns out that this total inversion charge that gets created is not very high in magnitude, this particular charge compared to this depletion charge. So this term can be ignored in respect to this term, which gives us this formula for the threshold voltage, which includes this flat band voltage, plus we can evaluate the depletion charge at 2 phi f based on the formula that we derived in the depletion, where we substitute psi s as 2 phi f in that formula and we get the depletion charge. We know the capacitance of the oxide in terms of epsilon of the oxide and thickness of the oxide plus 2 times psi f, which we substituted here. So this is this textbook formula for threshold voltage. It is beyond this voltage that inversion occurs, and that inversion leads to this formation of this inversion channel, which can now conduct. Obviously, at this point, it cannot at the threshold, it cannot conduct that much because it is just as n-type as this was p-type. But the more you increase it beyond the threshold, the stronger n-type it becomes and the more easily it can conduct. Cool. So yeah, that's the formula for inversion. So I hope it's now clear how, in principle, a MOSFET works, where you have this band bending. When it happens beyond the extent by increasing the gate voltage, an inversion layer gets formed. That inversion layer can become, if you continue increasing the gate voltage, very strongly n-type, which means it can conduct very easily. And if it can conduct very easily, then if you take a drain and a source, which are just technical names for terminals across which you apply a voltage, then that inversion layer can conduct from the drain to the source, which means that when the gate voltage is high, the MOSFET can be on and conducting, and when the gate voltage is low, the MOSFET can be off and non-conducting because you no longer have that inversion layer. So this is the principle on which a MOSFET works. I hope you're clear with that. Given that you are, we are now going to try and talk about this IV characteristic of the MOSFET. Let's move on. Cool. So, the first thing I want to do in terms of getting to the IV characteristics is okay, let me just explain you the structure. So, this is one terminal of the MOSFET, this is another terminal of the MOSFET, and this is the gate. To be technical, this is called the drain, this is called the source, but nobody really cares. It doesn't really matter what you call which terminal. What matters is that you have these different terminals in the MOSFET. The first thing that you want to do, and this is your channel, your channel essentially exists here. These bars don't represent your channels. You are coming to the bars. The bars actually represent the charge density, but your channel is in the middle. This is your gate. This is where you apply the voltage to turn on and off the channel. Now, your drain, this terminal you apply a voltage. For a positive voltage that you apply, this essentially conducts electricity from right to left if the channel is formed. Now, the first thing we want to do is we want to write the inversion charge at all these locations. Now, the threshold voltage was essentially used up in creating the inversion layer. So the threshold voltage does not constitute an additional charge in the inversion layer because the threshold voltage was essentially used up to make that depletion layer which we were talking about. So any charge, any voltage excess of the threshold voltage applied to the gate uh, creates this inversion charge when you multiply it by the capacitance. But if you notice in this expression, firstly, this is a per unit area expression. So this is charge per unit area, this is capacitance per unit area, just to be noted. But if you notice in this expression, we are also subtracting the net voltage by some term V of X, which is we are calling the local potential in the channel relative to the source. The issue is that we also, the reason we need to include this is that we also have a voltage drop from left to right. We don't just have a voltage on the top, we also have a voltage from left to right. That voltage is 0 here and VD over here. So according to the position, that voltage is also going to play into our net expression and it's going to essentially subtract from this Vg minus Vth voltage. So essentially what we mean is that so generally speaking, this terminal of yours is grounded. So when we are applying Vg, we are applying it with respect to this terminal. So at this end, you get the complete Vg minus Vth corresponding charge. And since this end has a voltage here, so as you move towards this end, you need to subtract by that voltage. So this local potential is essentially what gives you that. Cool. So this is your expression for inversion charge. The minus sign is because this is made of electrons, right? And this is the capacitance of the oxide layer. Cool. So this represents the charge that you have across the channel. Next thing we want to talk about is the gradual channel approximation, which basically says that the variation of the voltage along the channel is much slower than across the oxide, which basically we're trying to say that uh, we can treat this vertical electric field and this lateral field independently and kind of add their voltages in that sense. So that's the gradual channel approximation. Cool. Now, yeah, the next thing we want to do is we want to talk about current, right? Because ultimately we want to relate I to V. Now, uh, current, we know that in this case there is no diffusion that's really happening. Current is basically just happening in the form of drift. Now, you can just recall the basic formula of drift for current density, which was J is equal to N times the charge, electronic charge, times the drift velocity, where N was the number of charge carriers. So you can just do some manipulation of that charge. We know the drift velocity is mu times the electric field. You know that this is like yeah, you have width coming in, you have charge per unit area coming in. So you can just make like you can do the algebra yourself, and you can show that that expression for the drift current is equivalent to basically this expression. And from here we can substitute the we can essentially substitute the charge which we derived on the last page, and this is essentially the electric field, because we are treating, remember, this horizontal electric field separately from the vertical electric field. So this is what's going to cause the drift, right? So we then get this expression for current, and we are what we are basically going to do is we're going to take dx to this side, and we're going to try and integrate both sides to get the expression for the current. Cool. So we take dx to that side, we integrate, and we essentially take Vx as going from 0 to Vd. So Vx we just approximate it as a linear function. So we just replace it with V. So we just say that from 0 to Vd, it just goes according to the voltage at that point, right? So yeah, this is how we are going to integrate it. And so you just approximate it as linear from one terminal to the other, and you're integrated from 0 to the Vd. And once we integrate, this is the final expression we get for the drift current. So what we were trying to solve for was obviously the relationship between ID and VD, more precisely VDS, but because S is grounded, we are writing it as VD. And this is the final expression that we get for the current. Uh, Now, few caveats that I want to add to this expression. Firstly, if any part of the derivation was unclear, you can reach out to me, or you can like rewatch it. We were basically just we just wrote the charge as a function of distance, and then spoke about how that charge, due to that charge dense like surface charge throughout this channel, you're going to have drift according to the electric field that is set up in the channel, and we just essentially treated the vertical and horizontal electric field separately, and we just used that expression for drift and integrated it to get the current, the drift current. That's all that we essentially did in this. And this last step of integration was just that at the source you're gonna have 0, at the drain you're gonna have VD, anywhere in the middle you're gonna have V. You're just integrating with respect to Vx, right? Yeah. So yeah, I hope there are no doubts in this derivation. So this is the final expression we get for current. Now, few caveats I want to mention in this is obviously only valid when your gate voltage is more than your threshold voltage. That's the first caveat. The second caveat is that for a given gate voltage, you have one curve that you can draw between the drain voltage and the drain current. By the way, don't get confused by any of the names. You can just think of it as voltage and current. It's just technical term is drain voltage, drain current. Cool. So for each gate voltage, you have a specific curve. We'll see how those curves look in a second. And so essentially you have a family of curves with respect to what the value of gate voltage is. And obviously, if your gate voltage is higher, that curve is going to be above the lower gate voltage curve. Cool. Final caveat, which you can see over here, which is that if at your drain you have a voltage that is more than Vg minus Vth, you're essentially going to nullify the voltage that was created like the charge that was created due to the voltage at the gate. And what that nullification essentially means is that your channel gets pinched off at that point or no longer has charge in the channel. What that means is that beyond that point, if you increase your drain voltage, you don't get more current because your channel itself gets pinched off. And so that is why at that point you have saturation. So look at all of this again in the graph on the next slide. Cool. So this is the graph. Of course, we are plotting VGS VG minus V threshold on the x-axis, and on the y-axis we are plotting the current. Of course, when it's less than the threshold, we are not going to have any current because the MOSFET is switched off. Uh, when it's more than when the gate voltage is more than the threshold, depending on the gate voltage, we get a different curve for the MOSFET with respect to this drain voltage. Finally, when our drain voltage reaches this value of Vg minus Vth, this channel gets pinched off at the drain, meaning that there is no longer any charge at the drain, which means that even if you apply more voltage at the gate, it's not going to make a difference in terms of how like how much current you get because your channel itself gets pinched off, which is why at the point where your drain voltage becomes equal to Vg minus Vth, you have this saturation, and at saturation, after saturation, the current doesn't change. And this is the value of the current at saturation. It depends on the square of the Vg minus Vth, but it's constant with respect to the drain voltage. Now, uh, what I want to finally bring to your attention is how this relates to the operation of the MOSFET as a switch. Now you know that when your gate voltage more than your is less than your threshold voltage, you're not going to have any current, which means it's going to be off. And finally, you also know that if your drain voltage is more than Vg minus Vth, you're going to get this constant current, irrespective. Sorry, when you are in your saturation region, beyond this current being Vg minus Vth, irrespective of increasing, you're going to get this constant current. So you can talk about the saturation region as being on. You can talk about the uh, when the gate voltage is less than the threshold voltage as being off. So essentially, depending on the gate voltage, you can get these on and off states, and you need not use this intermediate region at all. So this is how you essentially get on and off from these curves of the MOSFET. So I hope the way MOSFET now works is clear. You can rewatch the stuff we discussed. You can refer to sources and all. But yeah, that was all from my end pretty much. Cool. So key takeaways from this module, the kind of band diagrams for MOS devices, how we drew them, how the channel is formed, how channel formation leads to behavior as a switch, which means that when you apply the gate voltage, the inversion channel gets formed, which can conduct, which means that when you apply voltage across the ends, it conducts current through it. When you don't apply the gate voltage above the threshold, the inversion channel does not form, which means that it's like an off switch. And finally, we learned about the MOSFET IV characteristics. Cool. Last final thing before we end the module as well as the course, I'm going to talk about some projects that you can do.
Of course, this entire module was optional. The projects are also obviously optional. You can work on them if you are interested. You can reach out to me if you have any doubts or if you need some help regarding that. So there are two projects that I'm proposing you do. So I'll get into them one by one now. Oh, before I get into the projects, I have listed some references here for further reading if you're interested. I'm pretty confident that if you're able to follow along this course, then you'll at least be at the level where you'll be able to read and understand any of these books. This is typically, I can't pronounce the author's name, but it's typically regarded as the quote unquote Bible for semiconductor device physics. Cool. So, on to the projects. So, first project, you can use something like MATLAB or Python. The stuff that we discussed in today's module is just essentially that, a MOSFET of that type. You take these values as input from the user. You take some phi values of gate voltage and you solve for these ID VDS curves and you display them. Okay, so it's not as simple as it may sound. You need to calculate, use these values, calculate the threshold voltage, do all of that, plug it into this expression that we derived, and do the plotting on these graphs. So, if you follow along this module or refer it, this project should be fairly simple and it should be illustrative for the MOSFET. Uh, a more complicated project that I am suggesting is that uh, I want you to basically design a MOSFET of your own that is on for this VG equal to 10 volts and off for VG equal to 0 volts. So it conducts when you apply this VG, it does not conduct when you apply this VG. So you just choose different parameter values, you design such a MOSFET. That's the first task. The second task, if you remember in the first module, I discussed how you can design logic gates like AND gates purely using switches. So I want you to use this MOSFET to design an AND gate based on defining logic level of 1 as 10 volt and 0 as 0 volt. You design an AND gate. Similarly, you should try to design an OR gate and a NOT gate as well. And like for this project, you can take help from the internet, see how these things are designed and all. It's meant to be for learning. Finally, you use AND OR and NOT gates, design an 8-bit full adder. You make a report compiling how you design the MOSFET, how you use that to design the gates, and how you use the gates to design the adder. And I guess you can claim that you've understood and designed your first calculator from scratch because you designed something that can on hardware implement one calculation based on the inputs given by any keystrokes, right? So it's essentially from understanding the physics to having a working quote unquote calculator that can just do addition. It's something that you can do. I think it'll be satisfying. So that is the projects. That's all from me for the course. I hope you guys enjoyed it. You can reach out to me if you have any doubts. Bye bye.